This is a video that you should watch as you read section 4.2 and try to work on the problems in there. It's about the forced harmonic oscillator. But compared to section 4.1, we're going to have a more realistic kind of forcing function on the right-hand side. Usually you want the right-hand side to be some kind of trigonometric sinusoidal input, that kind of forcing function, rather than an exponential decay. It's a little bit more realistic to what you use the forced harmonic oscillator for. Section 4.1 is a little bit easier to deal with. The exponential right-hand side is a little bit easier to deal with, but this is a little bit more realistic. That section introduces the topic. It talks about the method. This section takes it a lot further, and we end up using complex numbers in a real cool way. It does, in a sense, involve a little bit more work, or a little bit more complicated work at first, but it really reveals some features of the solution in ways that are real nice. So here's the example we're going to consider. Y double prime plus 6y prime plus 8y, typical left-hand side for a harmonic oscillator equation, equals 2 times cosine of 3t. So that's our forcing function over on the right-hand side. The overall general approach is the same. First, we want to look for YH, the solution to the associated homogeneous equation. Not the original equation, but the associated homogeneous equation. Think about the characteristic polynomial. You can use either S or lambda, it doesn't matter. When we guess these scalar solutions, that typically end up using S. There's the characteristic equation. Eigenvalues are going to be -6 plus or minus square root of 36 minus 4 times 8. It's minus 32 over 2. I guess I could have factored this one too. -3 plus or minus square root of 4 over 2. -3 plus or minus 2 over 2. Excuse me, a mistake here. -6 plus or minus 2 over 2. So you'll get -6 plus 2 over 2 will be -2. And -6 minus 2 over 2 will be -4. So YH is going to be an arbitrary constant K1 times e to the -2t plus another arbitrary constant K2 times e to the -4t. Nothing new there. Okay, there we have a typical kind of YH exponential decay. Where the real fun begins is with YP, a particular solution. Thinking back to the original equation, the original non-homogeneous forced equation, and thinking about the right-hand side, it would make sense to guess something involving cosines and perhaps sines. In fact, maybe an arbitrary constant times cosine of 3t plus another arbitrary, undetermined constant, I shouldn't call it arbitrary, an undetermined constant times sine of 3t would be a good guess. And in fact, that guess can be made to work, and you can solve for the 2 undetermined coefficients, and it would be fine, but we're going to end up using complex numbers in kind of a strange way, even in stranger and more fun than in Chapter 3. And in doing so, we're going to focus on one undetermined coefficient that's going to end up being a complex undetermined coefficient. What we're going to do is we are going to take our original forced equation and complexify it. We're going to create the associated complexified equation. Why would we want to complexify it? Well, hang with me, it's pretty neat how it all works out. What we're going to do is we're going to take the original equation, keep the same left-hand side, y double prime plus 6y prime plus 8y, But when you have a trig function, either a cosine or a sine, like we do here on the right-hand side, for the complexified equation, we're going to essentially, well, we're going to convert this to an exponential function where the exponent involves I, the imaginary unit, square root of negative 1. How so? Well, keep the coefficient 2 here as it is. And this is a cosine of 3t to the right of it. If it were a sine of 3t, either way I do the same next step. Convert it to an e raised to the I times 3t power. You're going to raise it, you're going to take e and raise it to the I times whatever the argument of the cosine function here is on the right-hand side. Or if it were a sine function, we'd do the same thing. We convert it to an e to the I times whatever that argument is, in this case a 3t. Why do we do this? We'll eventually see. But what I want to point out now is that by Euler's formula, this thing right here is really 2 times cosine of 3t plus I times 2 sine of 3t. And so therefore, the original right-hand side is really the real part of this new right-hand side for the associated complexified equation. The original right-hand side is the real part of this new right-hand side for this new complexified equation. If the original right-hand side had been 2 times sine 3t, then that would have been the imaginary part of this new complexified equation. What we're going to end up doing is we're going to end up guessing a solution to this complexified equation as an exponential function. And in the end, once we figure out what exponential function works, the real part of that will be yp for the original equation. We picked the real part because our original equation has a cosine on the right-hand side. If it had been a sine on the right-hand side, we would end up picking the imaginary part of the solution of this complexified equation. Got that? If the original equation is a cosine on the right-hand side, you pick the real part of this. If the original equation is a sine on the right-hand side, you pick the imaginary part of the solution of the complexified equation. There is a justification given for that in the book, in section 4.2, of why you should do it that way. I'm not going to take the time here in the video to do that. You should make sure you read about it and understand it and be able to reproduce it on an exam and relate it to your homework. So, let's go about the task of guessing a solution of this complexified equation, and then we'll take the real part of that solution. I'm going to call my guess y sub c to distinguish it from yp for one thing. That'll relate to my original equation. The c here also stands for complexified equation. One nice thing here is we only have one undetermined coefficient, though it will end up being a complex number undetermined coefficient. We'll call it a. What should I guess? Well, this is an exponential right-hand side. Guess an exponential. Guess an exponential involving e to the I times 3t, or I'll just write that as now e to the 3it. But you can think of it as I times the quantity 3t if you like. Approach it in the same way you did for problems from section 4.1. We've got to plug the guess in to the differential equation, so we've got to take its first and second derivatives, and assuming the derivative rules work for complex numbers as usual, and they can be defined to work that way essentially, we differentiate these, and we need to use the chain rule, so that gives us an extra factor of 3i each time we differentiate. So we get 3ai e to the 3it for the first derivative. The second derivative, I'm going to get another factor of 3i, giving me 9i squared a. I squared converts to negative 1. So that just becomes a negative 9a e to the 3it. Now, plug it in and solve for the undetermined coefficient A. Plug it into the left-hand side, yc double prime plus 6yc prime plus 8yc. I'm going to skip a step here, do this in my head. To make sure you don't make a mistake, you probably want to fill in a little bit more detail. I'll get a negative 9a is my coefficient of e to the 3it there. A plus 18ai, because I'm looking down here and multiplying that by 6, plus 18ai e to the 3it, and then a plus 8a e to the 3it looking here and also right there. The parts that don't involve an I, therefore, are the second derivative and the first and the original function. I'll group those together and factor out. Well, simplify. I'll get negative a e to the 3it. This is an a here, not a 9. Negative a e to the 3it. The part that involves an I will be from the first derivative term. There will be a plus 18ai e to the 3it. Ultimately, we want to set that equal to 2e to the 3it. That was our original right-hand side of this complexified equation. By factoring out what's in common here, that's equivalent to saying we want negative 1 plus 18i times a times e to the 3it to always equal 2 times e to the 3it. And therefore, the coefficient there must be equal to the coefficient there. We want these to be equal for all t, and that'll happen if and only if those coefficients are equal, and therefore we can solve for a as 2 divided by negative 1 plus 18i. In order to make this useful for us, we want to write this in standard form. This is really a division of complex numbers, 2 divided by the complex number of negative 1 plus 18i. The trick of multiplying the numerator and denominator of this by the complex conjugate of the bottom will convert it to standard form where the I is on the top. On the top, I get negative 2 minus 36i. And on the bottom, the great thing about multiplying by the complex conjugate of the bottom is that it makes the bottom real. When you multiply a number by a complex number by its complex conjugate, you're going to get a real number. The i's are going to go away. Think about it. You've got two binomial expressions here that needs to be FOILed. The outside and the inside terms will cancel. Think about those. The product of the outside terms is negative 1 times negative 18i. That's plus 18i. And the product of the last terms is 18i times negative 1. That's minus 18i. The outside and inside terms will cancel. The first and last, you have negative 1 times negative 1, which is plus 1. And then 18 times 18 is 324. And there's going to be a minus sign there from plus times minus, but then there's an I squared giving us another minus 1. So we ultimately get plus 324. Think about that for a minute. Do that on your own. Maybe pause the video. Check that calculation on your own. Once you've got this, it's a good idea to write this in terms of its real and imaginary parts. You can separate the fraction like this. Negative 2 over 325 minus 36 over 325 times I. So if we've done all our work correctly, and we have, this should be, when we plug it into YC, It'll be the value of the complex constant that makes this complex valued function, formally speaking, a solution to this complexified equation. And we'll want to take the real part of it to get yp for the original. So let's do that real quick. Can we find the real part? I'm going to go ahead and find the real part without bothering to simplify yc completely. I want to know the real part of this number a, negative 2 over 325 minus 36 over 325i, times e to the I times 3t, which by Euler's formula is cosine of 3t plus I sine of 3t. RE stands for real part. That's going to be my yp. It's going to be the real part of this product here. Think about that. The real part is going to come from the first and last when you do the FOIL method. The outside and inside products will involve an I. They won't cancel this time, but they will involve an I, and they will be the part by the I will be the imaginary part. That would be the yp if my original right-hand side was 2 times sine of 3t. But I want the real part because my right-hand side is 2 times cosine of 3t. So all I need to think about here is the product of the first times the first and the last times the last. First times first gives me negative 2 over 325 cosine of 3t. And last times last, I get a negative sign there and a plus sign there giving me a minus sign, but I have an I squared giving me another minus sign, so I ultimately get a plus 36 over 325 sine of 3t. And if you had guessed a times cosine of 3 plus b times sine of 3t, again, a times cosine of 3t plus b times sine of 3t originally for yp, you would have gotten the same answer. You would have found your two undetermined coefficients to be these two numbers. So the final general solution is, as usual, yh plus yp, k1 e to the negative 4t, excuse me, 2t is what I had. It doesn't matter, but I'll be consistent with what I had earlier. K1 e to the negative 2t plus K2 e to the negative 4t plus this thing, and I'm not going to bother writing that out. And you should be able to answer questions like, what happens to this solution as t goes to infinity? Because we've got a damped harmonic oscillator here, we do have exponential decay in the YH. That goes to 0 as t goes to infinity, and ultimately you approach yp, the forced response, or steady state response as t goes to infinity. All solutions will approach this function. So in fact, the yp, in a sense, is the most important part of the solution, since this part decays. It's transient as t goes to infinity. It goes to 0, and in fact, very rapidly. So we want to know about yp. What does its graph look like? Well, certainly you can use your calculator or Mathematica to draw it. But let's see if we can figure it out without Mathematica first, and then we'll check our answers. In fact, that's the benefit of using this complex number approach. This complex number A, what we'll see is it'll somehow encapsulate what the graph of this looks like. This is a sinusoidal function, and in fact, you can use trigonometric identities to write it as just a cosine or just a sine, although it's a cosine or sine with a different amplitude than either of these, and a certain phase shift to the right or left along the horizontal axis. That amplitude and that phase shift are somehow encapsulated in this complex number. Let's see if we can describe how. The key is to figure out how to write this complex number in essentially polar coordinates. We can represent complex numbers geometrically in what's called the complex plane. The horizontal axis is labeled as the real axis, and the vertical axis is the so-called imaginary axis, but it is there. Your eyes are not deceiving you. Okay, it's just a way of representing essentially the complex numbers. Essentially, we're taking this complex number and we're associating it with a point whose coordinates are the real and the imaginary part of the complex number. So by plotting that point in the complex plane, we imagine that as plotting the actual complex number. It's a nice way to visualize it. Now, that number is going to be real close to the origin, but certainly the real part is a lot closer to 0 than the imaginary part. They're both negative, so we're going to be down here somewhere in the complex plane. If you know something about polar coordinates, if you don't know anything about polar coordinates, you'll want to look it up. You know that you can specify the location here in this plane by two other numbers than what is done usually. You can specify it by how far it is from the origin. That's the radial coordinate. And by the angle that that line segment makes with the positive horizontal axis. I'm going to call the radial coordinate r. So r is going to be the length of that line segment. And call the angular coordinate theta. There is redundancy with polar coordinates. You could use a different theta. You could go, instead of a counterclockwise rotation, you could go clockwise, and then you'd have a negative theta. Or you can add multiples of 2 pi to this. Let's see if we can figure out r and theta as we have them drawn. R just comes from the Pythagorean theorem, the distance formula. Sometimes we use absolute value symbols around our complex number in this situation to denote that distance. And just doing a little calculation on Mathematica. To find this, we again use the Pythagorean theorem. Equivalently, the distance formula, we need to take the square root of the sum of the squares of the coordinates for the point. In other words, the real and the imaginary parts of the complex number. So negative 2 over 325 squared plus negative 36 over 325 squared. Of course, those negative signs won't matter. Ultimately, in the numerator, we get a 4 plus 1296 is 1300. We get a square root of 1300 divided by square root of 325 squared, which will be 325. You could leave the answer like that, but you also can simplify it. For example, we can divide 1300 by 4 to get 325. Square root of 4 is 2. So we could write it like that. We can simplify it further because 325 is divisible by 25, which is a perfect square. 325 would be 25 times 13. Square root of 25 is 5. 2 times 5 is 10. So we could write this as 10 square root of 13 over 325. It's not a big deal. You can write it any one of these ways. That'll be our absolute value of the complex number, frequently called the modulus of the complex number. And the amazing thing is that this thing is the amplitude, believe it or not, of yp, of this function. Let's see if we can use Mathematica to believe this. First of all, let's let me just quickly double check my calculations. Square root of 1300 divided by 325, and numerical approximation for that is 0.11094. And this other form of it, 10 times square root of 13 divided by 325. I guess I could simplify that even further, divide top and bottom by 5. I'll do that on Mathematica. I get a 2 on the top and divide the bottom by 5, I would get 65. So that's another way to write it, and you can see it is the same number. But let's plot our original yp that we got a few minutes ago and see if it looks like its amplitude is about that number. So we got negative 2 over 325 cosine of 3t plus 36 over 325 sine of 3t. All right, here we go. Look at the scale here. The amplitude looks about right. It was, look at the very top, it was about 0.11. And that's where this is, about 0.11. Is there indeed a phase shift from, say, an ordinary sine or cosine? Well, yeah, just barely from a sine. If you look at this point right here, that's not quite going through the origin. It's a little bit to the right of the origin. So writing it in terms of sine, it's just a very small shift to the right. Our book focuses on traditionally writing these things in terms of cosine. Technically, you can do it either way. I guess we'll try to stay consistent with the book and write it as a cosine. How do you figure out the phase shift? Well, that comes from the angular coordinate of the point. Back over in this plane, the theta is going to help us determine the phase shift. How do you figure out theta? Well, once again, your trigonometry never goes out of style. Some trigonometry can help you figure it out. You can draw triangles and think about it. The quickest way to see it, what to do here, is to realize that you can use the arctangent function, essentially taking the arctangent of the imaginary part divided by the real part of the complex number. Though you've got to be careful because the arctangent function only gives you outputs between negative pi over 2 and positive pi over 2, or in degrees, between negative 90 degrees and positive degrees. If I take the arctangent of the ratio of these two, the 325s will cancel, the negative signs will cancel. I'll really get 36 over 2 or 18. But that will give me an angle in the first quadrant here that will be close to 90 degrees. To get the angle I really want, I need to add pi radians to that, which you can just see from the picture. So that will be the angle theta for this complex number. This is often called the argument of the complex number. The absolute value is usually called the modulus of the complex number, and the angle is often called the argument of the complex number. Let's approximate this. Arctangent of 18 plus pi. It's about 4.65689 radians, and that would be the units of t. It's radians if you're thinking of it as an angle, but in terms of the original quantity, it would be whatever the units of t are. The book talks about converting this to degrees, and that would be okay, though I think it's probably less confusing if you keep it in radians. I can take that previous output and multiply it by 180 over pi to get about 266.82 degrees, practically 270 degrees, which makes sense with the picture. As far as figuring out the phase shift, what you want to do now is think about this yc function. And you can write A in terms of its polar form like this. As its modulus times e to the I times its argument. E to the I times its argument. Why does this work? Well, I'll let you think about it for a minute. Basically use Euler's formula to write that as cosine theta plus I sine theta, and then use some trigonometry. R cosine theta is x, the x coordinate of the point, and R sine theta is y, the y coordinate of the point. I'll let you think about that. Because of this representation, by using properties of exponential functions, we can combine these two exponentials like this as e to the I times the quantity theta plus t. And then by Euler's formula again, we can write this as r cosine of theta plus t plus I r sine of theta plus t. And recalling that our yp was the real part of this function, this thing is yp. It is the same function. So that's telling us that we can represent our yp as r, the modulus, which I said was the amplitude, times cosine of, well, maybe write this as t plus theta. The theta, in a sense, is the phase shift. Oh, I'm forgetting something here. I'm forgetting my 3. 3 in here. So in fact, I've got 3 t's in here. To really figure out what the actual horizontal shift is, right or left, I should really factor the 3 out of it. So yp could be thought of as r, which ultimately can be simplified to 2 square root of 13 over, what was it, 65, times cosine of 3t plus the arctangent of 18 plus pi. I guess I'll write this as the approximate form here. Arctangent of 18 plus pi being about 4.65689. To figure out how to see that as a horizontal shift, it's best to factor out the 3 inside that cosine. 3 times the quantity, t plus whatever. Well, whatever can be found by taking the 4.65689 and dividing it by 3. About 1.5223. Pi 523, excuse me, 1.5523. Okay. Cosine of 3 times this thing. Parentheses here. So what this is telling us is we could take the graph of cosine of 3t, squish it down by this factor, which is a small factor, and shift it to the, careful here, if you've got a t plus 1.5523, it's actually, can be best thought of then as a shift to the left from a cosine wave by that amount. If I also plot cosine of, well, I'll plot up here also about 0.11 a cosine of 3t in addition to the yp. And so this purplish reddish curve is that 0.11 cosine of 3t. You can see it starts at its peak over here. If I shift that to the left by 1.55 units approximately, I should be at the solution yp. And it does look about right. This is above 2 approximately, and this is above approximately 0.5. So if I shift this one to the left by that many units, I'll get the blue one. Of course, I can also shift it to the right. I guess that would correspond to picking theta to be arctangent of 18 minus pi, giving us a negative angle, and ultimately using the exponential property, seeing that as a 3t minus an angle, seeing it as a shift to the right. So this is a very nice way to see the amplitude and the phase shift without using too much trigonometry. Ultimately, what we're avoiding here is too much trigonometry. In the next section, section 4.3, it's going to pay even more dividends, where we end up talking about resonance and a phenomenon called beating. And it really will be a nice technique to understand that phenomenon. And that's the end of this video.